Okay. Okay. This is going to be a revision session for. Let me check this is on. Okay, it should be on. This is going to be a revision session for AQA Level 2 or further maths for the paper tomorrow. I have quickly glanced over paper 1. And what I've done, and I've glanced through some of the past papers. I say glanced though, but I've looked through them and I've tried to compile some questions that really haven't come up in paper 1. So it might be on paper 2, and I've looked at, and these are all from past paper questions. And so the idea of this session is to just go over them, okay? For the exam tomorrow. So if it helps you, it helps you. I had to have the fan on. I try to stay because it's very, as everyone will know, very warm at the moment in the UK. But I try to stay fairly far away. I don't know. Obviously, you still hear a little bit, but hopefully my voice or whatever, you still be able to hear it fine. Okay. But yeah. So let's get started, I guess. So question 1. We are given x plus 1, which is just a number, obviously. It's increased by 20%. Its value is now the same as x plus 6. Find the value of x. So this you're pretty much going to need to know multipliers. Okay, so we can say, for example, say we had 50, we wanted to raise it by 20%. Well, we're going to be timesing it by 1.2, aren't we? Because the 1.2, the 0.2 will represent 20%, right? Because 1 would be 100%. Okay, so remember, percent is just times by 100. So therefore, 0.2 represents 20%. If we're adding 20% on, so increasing it, it's going to be 1.2. Okay, and that's your multiplier. And so 50 times 1.2, for example, would be what? Like 60, I believe. Um, and so 60 would represent a 20% increase. We're going to apply that same concept here because x plus 1 is just a number. So there we go, so x plus 1, and then we're raising it by 20%, so times 1.2. It's now going to give us this number x plus 6. And actually, this is just a linear equation, right? Because now we can times the bracket by 1.2. So to get 1.2x, add 1.2 is x plus 6. And now we can solve it, okay? So I can bring the x to the left. To then say 0.2x is going to equal 6 minus 1.2, which is going to be 4.8. So therefore, x then is going to be 4.8 divided by 0.2, and that will get us 24. There we go. Cool. But yeah, so the main thing is just form an equation by using the multiplier. So increase by 20 means times by 1.2. Okay, 20% of this would be 0.2, but we're increasing it, so it'd be an extra 20%. Hopefully that made sense. Okay, question 2. Um, okay, it says the factorizes fully. Um, Okay, well, first of all, I notice I have an x and y common to both. So I can factorize an x and y to say this will be 6x, because we have another x here, plus 21, okay? But can we factorize further? Well, we're going to have to look at the coefficients, right, the numbers. So 6 and 21, is there any factors between them? Yes, 3 is a factor. Because 6 is 2 times 3, and 21 is 7 times 3. So then we can factorize further to then pull out of a factor of 3 to then say it could be 3xy of 2x add 7. And we can't do anything more with that clearly. So that should be our answer. Cool. So you just got to look for stuff to bring out essentially. There we are. Question 3. Okay, probably the first non-GCSE, normal GCSE maths question here. Okay, so we're given this matrix product and it's equal to k of I. Work out A and B. Okay, fairly typical. And yeah, so we need to work out this matrix product first of all. That's going to help us a lot, I reckon. So 2103 of A, B, 0, 0.4. So that's going to give us another 2 by 2 matrix. So 2 rows and 2 columns. So we're going to have 4 entries. Here, 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 and here, right? Let's work that out then. So for the first one, because we're in row 1, column 1, we're going to multiply the first row of the matrix, or the first matrix, by the first column of the second matrix. Okay. Remember, in general, a matrix is defined. Its size is defined by how many rows there are and how many columns. So we do rows and columns in that order. Anyway, so with that in mind, so for the first one, right, it's in row 1 and column 1. So first row by the first column, so it's going to be 2 of A, first of all. 2 times A, add 1 times 0, which is 0, so we left with 2A. Okay, now let's work with this one. So this is now in row 1 again, but now it's in column 2. So we need to work with the first row and the first matrix by the second column this time. Okay. So that's going to be 2 times B, so that's 2B. Add 1 times 0.4, which is just going to be 0.4, right? Um, cool. Now let's work with this entry here. So this is going to be row 2, column 1. And now this time we're going to look for the second row of the first matrix by the first column of the second one. Okay. Cool. So that's going to be 0 times A, which is 0, and then add 3 times 0, which is going to be 0 as well. So it's just going to be 0 there. Okay, now with this entry, that's going to be row 2 and column 2. So you want the second row of the first matrix or the second column of the second. And so then we times 0 times B, which would be 0, add 3 times 0.4, which is going to be 1.2. Okay. Um, and now we've got our matrix. Cool. And that's how matrix multiplication will work. Okay. At least for 2 by 2 matrices. That'll be pretty much the only matrix you'll deal with in further maths. Uh, but yeah, that's the sort of the way of working it out. Okay. So you consider the row and the column position, and then you use that to guide you to work out what row of the first matrix and what column of the second matrix you times by. Okay. Now with that in mind, we've got a matrix now, but we're told this is equal to k of I. Now you need to remember I, called the identity matrix, is 1001. Briefly, it's identity because it's kind of like 1 in the what's it called, in the matrix world. So for any normal number, right? Say for example, I don't know, A times 1, it will give you A. It's the same, and that's the role of the 1. Okay, it keeps it. If you times it, you get the same number. The identity will always be the same. So if we have a 2 by 2 matrix, any 2 by 2 matrix like this, times it by I, you will get. Oh, that's not I. You will get the same matrix back. Okay, so it'll be A, B, C, D. Anyway, that's just what that means. But you need to remember that's I. Okay. And so k of I, so we times it by a number in the front, well, we're just going to times each number inside the matrix by k. So that's just going to be simply k times 1 is k times 0 is 0, k times 0 is 0, k times 1 is k. That will be that result, so that will be equal to k, 0, 0, k. Okay, cool. Now we could just compare the entries, okay? So I can gather from this, the first entry here, 2 of A and K, that 2A has to equal K. Okay. Then with the second one, I can deduce that 2B and zero point 0.4 is 0 for the second entry. But actually, I can then get B from this, can't I? Because I can solve it. So that means 2 of B is minus zero point 0.4, so then B would be minus zero point 0.2 by dividing by 2. Okay, cool. Okay, now if we then convert the third entry, well, 0 is equal to 0, well, that's not helpful. But then what about the last one here? 1.2 in k. And so therefore 1.2 has to equal k. Cool. So now I've found k and b, now I can use this to find a. So therefore 2 of a is equal to 1.2, so a is going to be 0.6. And that is our answer. We need to find a and b. There we are. Cool. Okay. Question 4. Okay. Uh, Hang on. Let me get rid of this box here, so I can see the question. There we are. Let me draw the box. There we are. Okay. Question 4. So we're given a line A with this equation here. We're given B is parallel to A and passes through this point 2, 1. And we're given the point lies on B. Find D. Okay, so this sort of question, just break it down, do line by line. So we give an equation for A, and we're told B is parallel to A. So therefore, I can work some out already. If I know two lines are parallel, that means their gradients are the same. So I'm going to need the gradient of A. So A is y plus 4x equals 6. I need it in the form y is mx plus c to get the gradient n. So therefore, y is going to equal minus 4x at 6. So therefore, the gradient is minus 4. Now, that's a gradient of A, but B is parallel, so it has the same gradient. And as A parallel to B, gradient of B is also minus 4. But therefore, then I could say that y is going to be equal to minus 4x at C for our line for B, okay? But bear in mind, the one set, the C, will be different, okay, to A. But how would we find C? Well, we're given the point 2, 1. So I'm going to say then, what am I going to do? I'll do it here. Sub 2, 1 in. So that means y is 1. So 1 would equal minus 4, lots of 2 at C. So therefore C, well, that's going to be 1 equals minus 8. So C is going to be 9, right? Because then 9 minus 8 would give us 1. Okay, but therefore then, we've got the complete equation, minus 4x plus 9. Okay, but then what's it saying? The point D lies on B, find the value of D. Well, we have the equation for B in, so we can substitute, let me get rid of this now. We can substitute the point in and to see what we can do with it. So D in 2D, but Y is 2D, so 2D is going to equal minus 4. Now X is D, so it's going to be minus 4D at 9. Well, again, this is a equation, right? So we can solve it. So that means then if I add the 4D across, that's 6D is 9. So D is going to be 9 over 6, which should be do, 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 uh, 3 over 2. Right? I don't know why this took me so long to figure out. Yes. So that all 1.5. But there we are. Cool. So the answer 1.5 or 3 over 2. Okay, cool. Question 5. Okay, very typical as well. What I've noticed anyway from glancing seems to come up these sort of composite functions. So we have three different functions in the same one. You know what I mean? So we've got three different expressions for x here. Um, but the key takeaway is that there are for different values of x. We are given this function here, and we need to find all the values when f of x is minus 12. So what that means is, well, the best way to do this is to equate all three individual parts to -12 and solve it and see if we get a solution. So let's do the first one. So that's going to be 4x then. That's the first equation, 4x. So that's going to equal to -12 first, because that's going to be f of x. So then x then is going to be -12 and 4, which will be -3. Now we need to check as well, is this valid? So because all these, I guess mini functions, right? Mini express parts of x, they're only valid for certain values of x. So the first one is defined as x less than 0. But here, so minus 3 is less than 0. So therefore x minus 3 is a solution. So that's the first part. And then we need to do the same for the second part. So then x squared minus 8x again has to equal -12. So we're going to solve this. So x squared minus 8x add 12 equals 0. Does it factorize? Let's have a look. 12 and 1, 6 and 2. Yes, they do. Because then if you take -6 and -2, they times to give 12, because negative times a negative positive, but they add to give -8, so there we are. Alternatively, because you do have a calculator, you could use quadratic formula, but yeah. I notice this factorizes to x minus 6, x minus 2, so therefore x is 6, x is 2. Now I need to check again, because this is valid between 0 and 8. Well, actually 6 and 2 is between 0 and 8. So 6, so I'm going 6 and 2 is between 0 and 8. Again, so these are both solutions as well. Okay. And so then the third part, we need to consider the third like mini function, 6 minus 2x. So 16, sorry, minus 2x has to equal -12. Um, and then we can solve it. So well, 2x is going to equal 28. If I add the 2x to the right and the -12 to the left. And then 16 add 12 is 28. There we go. Therefore, x is going to be 14, right? Divide by 2. Again, the third part is to find when x is greater than 8. Well, 14 here is greater than 8. So again, that's also a solution. So x equals 14. Well, those are our four solutions then, right? So it's going to be, the first one was -3, wasn't it? I believe. Yes, so -3. Then we had 2, 6, and 14, right? Yes, and those are our four solutions. If, say for example, in the second one, but in this case, all the numbers worked out nicely. They all were valid. But say if you had one solution in this interval, say for x squared minus 8x, say if you had x was 10, well then 10 is not between 0 and 8, it's above 8. So that wouldn't be a solution, okay? Um, but in this case, it was all worked out fine. And you can, so I had to go over the graph. Notice how they sketched it as well, in case it might be a different question asking about sketching. 4 of x is the first part, so you have to draw that when x is less than 0. So 4x will obviously look like this sort of equation here of a line. Oh, not like that. It has to pass through 0, like that. But here, so you notice this part here, that looks like this part here, right? This little on the negative part. But here, you're cutting off all the parts where x is greater than or equal to 0. So that's this first line here. Then this little quadratic part here. Um, Again, you're going to probably sketch x squared minus 8x between 0 and 8. So when x is 0, the quadratic is 0, and when x is 8, um, the quadratic will be 64 minus 64 is 0, so it goes back to 0. Then you need to pay attention to where the dip is, because obviously a quadratic, if it's a positive, it's going to look like have this sort of shape, isn't it? Which we can see here. That's like a smiley face shape. So you have to pay attention if there's a minimum, and in this case there is, but they've told you this. If you needed to know where the minimum was to see where the graph dips, you should complete the square. So then x squared minus 8x would be x minus 4 squared minus 16. And you can see that here, the x coordinate before minus 16, and that's the turning point. Okay, so you've got our two endpoints, 0 and 8, and the minimum where it dips here by completing the square. That allows us to complete that quadratic part. And then this final part again is going to be another straight line, isn't it? Minus 2x adds 16. So minus x would look like this, or minus 2x. But then we shift, but then there's a y-intercept of 16. So we're going to shift it up here pretty much, which again is what we can see here. It kind of matches the line that we've got. But then we need to sketch that from x greater than 8. So when x is 8, 16 minus 2x will get 16, 2 to 2x is 16, so 16 minus 16 will get us 0. And we can see that here. So it starts at 0, then it goes down, like we can see here. And that's how we get that graph, okay? Because I have seen a question that actually to sketch a function that looks exactly like this. So that's the process, and that's how they got this graph here. Anyway, so that cool. So the main component is to not freak out and just split it up one by one, okay? So deal with all these three mini functions separately, like we just did. Okay, cool. Question 6. Okay, we are given this expression for y. Find dy dx, so differentiate. Okay, well, you should be able to differentiate a polynomial that looks something like, I don't know, 3x squared add 6x cubed add x add 5. Something like that. Okay, that's what we need to get it into. But it's not that simple here because we have some sort of product here. We're timesing x to the 4 by something else. We need to get it exactly like a polynomial. And the way we're going to do that is, well, times out the bracket, right? It's a good idea to always expand or multiply out brackets to see what we got. So if we did multiply it, so that's going to be 2x to the 4. Again, you can use FOIL or whatever you want, but hopefully at this sort of level, you should be fairly confident with expanding brackets. But in this case, we have 2x to the 4 times x cubed. Now that's going to be the power, the index floor, right? If we times in x to the 4 and x cubed, you're going to add the powers, right? So it's going to be 2 lots of x to the 7. Okay, and that's our first bit. Then we can expand 2x to the 4 times 2 plus 2. So that's going to be 2 times 2, which is 4x to the 4. And then we're going to have minus 3 over x, add 2x to the 4. So 2x to the 4 times by minus 3 over x. So that's going to be minus 6x to the 4 over x. And the x will cancel. So it's going to be minus 6x cubed, okay? And now this is a polynomial, right? Expression, which we know how to differentiate. Cool. And so in general, each polynomial term, in this case 2x to the 7, when you differentiate something like this, that's going to go to, well, first of all, you have to times the power with the number in front. So it's going to be 2 times 7, which is 14, x, and then you knock 1 off the power, okay? X to the 6. So then dy dx, if we differentiate every term here in that way, so again, that's going to go to 14x to the 6. Then 4x to the 4, again, you times the power by the number in front, so 16, x, and then x, and then you knock 1 off. So 4 minus 1 is 3. In the same way, minus 6x cubed, again, you times the 3 by minus 6 to get minus 18x. And then knock 1 off. So 3 minus 1 is 2. And that is your expression there. Cool. Great. Okay, question 7. A is a value greater than 1. Work out the value of m for which this ugly looking expression occurs when it's equal to each other. Okay, well, let's just simplify this ugly thing. So this screams this power law here. So if you have a to the b of a to the n of m in particular, you're going to times the powers, right? If you have something in the bracket raised by a power, you times the powers together. Okay. You should remember that from normal GCSE. Okay, so with this in mind, a to the n to the 4, it's going to be a to the 4m, because then n times 4 will be 4m. And then this is going to equal to a to the 5 of 2 of them, so you're going to times 5 by 2m. 2m times 5 will be a to the 10m. Okay, now we can compare, right? Then we can say, well, 4m is going to equal 10m. Um, and so I believe m is 0. Is that right? I assume so, because then you'd get 6m is 0, so therefore m is 0. Let me check that. That seems a bit weird to me. Uh, Interesting question. By the way, all these questions, if you are interested or stuck on a particular question and you want to see where it comes from, see the mark scheme or whatever, I've noted all the questions where they came from in that way there. Okay, let me check this though. Yep, m is 0. Okay, I thought that was weird. Okay, yeah, that is right. Uh, okay, that's interesting. Okay, then for part B, um, okay, but again we're given this ugly expression as well. Write y in terms of w and x. Okay, let's have a look. So w cubed x squared y to the 5 is w to the 13 x to the 7. So there's only one y here, so we have to rearrange for y. Well, we have y to the 5, so we can say y to the 5 is going to be w 13 x to the 7. Now we're going to divide by w cubed x squared, because this is almost like saying w cubed x squared lots of y to the 5 is w 13 x to the 7. So then we divide by this part to get rid of it, to just be left with w y to the 5. Okay. Um, okay, but we can simplify this division because of the power law. A to the m divided by a to the n, you subtract the powers, right? So let's start with w. W 13 minus 3 will be w to the 10. And then x to the 7 minus 2 is going to be x to the 5. Okay, cool. So that's y to the 5. Then to get y, not y to the 5. Well, how are we going to do this? Well, I noticed, well, you can, with equations, you can raise it to different powers on both sides. But to undo the 5, I'm gonna want to do y to the 5 of a fifth, right? Because then if I times 5 by a fifth, you get 1. To be left with just y, right? Y to the 1, which is just y. And I'm going to do the same here. So it's going to be w to the 10, x to the 5 of a fifth. And then how are we going to work that out? Again, if we raise something in a bracket by a power, we times the powers together. So in this case, a 10, 10 divide times a fifth, well, 10 divided by 5 is going to be w to the 2. And then x to the 5 times the fifth is just going to be x to the 1, or just x. And that is your expression there. Cool. Okay. Question 8. Prove algebraically that when n is an integer, this thing is always even. Well, again, like I said earlier, it's best to just expand and simplify the brackets first to see what you're dealing with. So, 2n plus 1 squared minus 2n minus 1 squared. Well, when you're squaring a bracket, you times it by itself, right? So we have 2n plus 1, lots of 2n plus 1, so it repeats, minus 2n minus 1, 2n minus 1, and then we should just expand this. So that's going to be, again, you use FOIL or whatever, but it's just an expanding bracket exercise, really. So let's expand it, so you're going to get 4n squared, then you're going to get 2n plus 1, should be 2n, add another 2n, which would be times 1, which is 2n, add 1 times 1 is 1. Well, actually, this simplifies to 2n, and 2n goes to 4n. Okay. And then minus, and then I'm going to put a bracket here, because I'm going to expand this whole thing, and then I'm going to minus everything afterwards. So let's expand what's in the bracket. So 2n times 2n is again going to be 4n squared. Then 2n times minus 1 will be minus 2n. And then I'm going to times minus 1 by 2n, should be minus another 2n, which obviously will go to minus 4n overall. And then minus 1 times minus 1 will again be positive 1. Okay, but now I'm subtracting. So I'm subtracting, so it's going to be 4n squared plus 4n plus 1 minus 4n squared minus lots of minus 4n, which should be positive 4n, because it's like you're times in negative 1 by negative 4, which should be positive 4, and then minus 1. And now things should cancel. And actually, but the 4n squared with minus 4n squared would go to 0, so they cancel. 4n and then add 4n would just be 8n. And then 1 minus 1 would cancel again to 0. So we're left with 8n. So therefore, this whole fraction, right? 2n plus 1 squared minus 2n minus 1 squared over 4. Well, this whole bracket at the top just equals 8n. And that's over 4. And then 8 divided by 4 goes to 2. Lots of n. Well, it's always even because we're multiplying an integer n by 2, and this is in the form of an even number, as it is a multiple of 2. Cool. Question 9. Okay, use matrix multiplication to show that a rotation 90 degrees anti-clockwise followed by reflection in the line y is x is equivalent to the reflection in the x-axis. Right, okay. There are some transformations with matrices you need to know, reflection, rotation, stuff like that. You can learn them, but I guess let's go over another way of doing this. So, you need, from what I've seen anyway, you need to consider a unit square. So, a unit square is essentially a square with sides 1, and it can go for, it starts at 0, 0, right? So, if it has a side length of 1, 1, 1, 1, let me redraw it then. It's a bit messy. That means this side is going to be 1 here, that's going to be 1, and this is going to be 1, 1. Okay, because we're going 1 in the x here, 1 in the x direction, and 1 in the y direction. So going 1 to the right, 1 up, so that'd be 1, 1. Okay, so we need to bear those coordinates in mind, right? And this coordinate, for example, here would be 0, 1, and here it would be 1, 0, and obviously the origin would be 0, 0 here. Okay, so this unit square then. Okay, so rotation 90 degrees anti-clockwise. Okay, so with this sort of question, if they give you the transformation, it's probably best to see how the unit square would look. Okay, so if we rotate it 90 degrees anti-clockwise is that direction. The square is going to look. It's going to go to here, isn't it? That'll be the transformed square. When you rotate it 90 degrees anti-clockwise. Now we need a matrix to represent that. There are probably multiple ways of doing it. The way I did it before I seen this, I did it algebraically, but I won't go into that. What you could alternatively consider is the identity matrix again, which is 1, 0, 0, 1, as you remember. Now, consider this essentially as two different coordinates, 1, 0 and 0, 1, right? This coordinate here, 1, 0, and this part here, 0, 1. Now, what you want with this is to consider specifically the coordinate 1, 0, which is actually going to be here, right? This 1, 0, and 0, 1, which is actually going to be here. So if I draw this again, this square, okay, so firstly, this coordinate, right, 1, 0, where is that going to go to when we reflect it 90 degrees anticlockwise, considering this reflected, where is it now? Considering the reflected square here, where would that point go to? It's going to go to here, right? It's going to be this point here. If you can imagine it, visualize visualize when you reflect at 90 degrees, right? It's going to go to here, and that new point is going to be well, 0 in the x1 and 1. Okay. So actually, then the matrix. So what happens? So it goes to 0, 1. Well, that'll be the first part of the matrix. And then okay, so we've seen what happens with the point 1, 0. Now we need to investigate what happens to the point 0, 1, which is going to be here, right? So if we get rid of this now, which is going to be this point here. So it's going to be 0, 1. So where would that be on the rotated square here? Where would that go? Well, it would be here, wouldn't it? It would be this point here, which would be -1, 0. Okay, if you can imagine that. Oh, okay, it looks a bit messy here. Um, so again, the square would go here. So that point here would go to here. Okay, if you can imagine, which is -1, 0. If that's the reflected vertex of the square. That's where that vertex would go to the new square. Okay. So it goes to -1, 0, which is obviously -1, 0. So it's going to look like this. Okay. And that is your rotation matrix, 90 degrees anti-clockwise. Okay, cool. Now, what about reflection in the line? So let's get rid of all this. And we're going to apply the same sort of method again. So, reflection in the line y is x. So again, let's consider this square here, unit square. We're reflecting it in the line y is x. So again, the y is x line is here. And again, you can consider what happens to these two particular coordinates, right? 1, 0. Again, 1, 0 is here. X coordinate 1, y coordinate 0. That's going to go to, if you think about here, it's going to go to this point here, isn't it? Which is going to be 1, 0. No, 0, 1, sorry. So 1, 0. So that's the, I should know, that's the rotation matrix. Now for this one, the reflection one, y is x. 1, 0, everything goes to 0, 1. So that's going to go to 0, 1 here. And then we need to do the same for this part. 0, 1. Now, well, that's this point here that I just circled. Again, if we reflect it, it's going to go back to this point, isn't it? If we reflect it in the line. So that will go to 1, 0. So that'll be your reflection matrix in y is x. Okay. So we've got these two matrices. We need to show it's equivalent to a reflection in the x-axis. Okay. But then we're going to need to know what reflection of the x-axis matrix is before we do anything else. So again, draw a unit square again, and again, consider what these 2 points on this unit square will go to. So 1, 0, first of all, will be here, right? If we reflect it in the x-axis, so this is x, it's going to remain where it is, isn't it? So it's going to be 1, 0 again. And then this point here, the next one, 0, 1, is going to be here. That's going to go down here, isn't it? If you reflect it in the x-axis here, okay? And that point will be 0, minus 1. So it's going to go to 0, minus 1. So that is your reflection in x-axis, okay? So I've got our three matrices, right? Again, it's up to you whether you want to memorize it. I don't know. It really is up to you. But that you can work it out this way, right? By considering the identity matrix. I think this is the simplest way of doing it anyway. And then consider that these two. Oh, that's the wrong identity matrix. There we are. And then you consider these 2 points, 1, 0 and 0, 1. And then you consider what those 2 points, how they, where they transform or where they transform to. Okay. And then that transform point will be part of the matrix, right? As we just done. So we've got our three matrices then. So let's get rid of this. So we need to show that this rotation followed by this reflection is equivalent to this. Okay. So these are combined transformations. So how are we going to express this? Well, think about in general, we have a point x, y. If we were to transform it, say with the rotation, it'd be 0, minus 1, 1, 0. So the matrix times by the point x, y. And that would give us, obviously, the transformed point. Okay. So in that respect, then, if we want to apply the rotation first, we're going to want the rotation matrix closer, right? So that means we want the reflection afterwards. So it's going to be 0, 1, 1, 0. Because then what this is saying is we are rotating the points, right? First, and then after that will give us this new set of points, and then we are reflecting it by the new set of points, okay, to get another set of points, if that makes any sense. So essentially the order is going to be this, right? And that's the matrix going to need to compute, okay? And then if we apply the matrix multiplication, again, now if we want the first this entry here, the first row and the first column, we're going to want the first row, the first matrix times by the column, the first column to second. So 0 times 0 is 0. And 1 times 1 would be 1. Okay. And then we say then if we want this point here, again, it's going to be the first row and the second column. So we want the first row here, cool. And then we want the second column to second matrix. So it's going to be 0 times minus 1, and then 1 times 0, it should be 0. Okay, and then what about this entry here? Well, we're going to want the second row and the first column. So the second row now will be there, and then the first column will be here. So 1 times 0 is 0, and 0 times 1 is 0. Okay, cool. And then for this point, obviously, it's going to be the second row and the second column. So the second row here, cool. And then the second column to second matrix. So we want to work out that entry. It's going to be 1 times minus 1, should be minus 1. Add 0 times 0 is 0. And that's the transformation that represents these two matrices here. Well, that is this matrix here, isn't it? 1, 0, 0, minus 1. So we've shown it. We've shown that rotation followed by reflection in y as x is reflection in the x-axis by matrix multiplication. There we are. That's a very difficult, very, very difficult question. That is very difficult. If you want those top grades, I would recommend having a look at this sort of question here. Hope and try and make sense of it. Alternatively, yes, you could just memorize it, but then you also need to know the order in which to multiply the transformations. In general, it's the first transformation, and it works your way out. So then you have the first one, then you have the second one, and then we have like the third or fourth. Then it would work your way back to the left. Okay, but yeah, but there we are. Cool. Um, Okay, question 10. Rearrange w is y squared of 5 of y squared minus 2 to make y the subject. Okay, so rearranging, we've got a fraction. The best thing is to get rid of the fraction, so let's times across. So w lots of y squared minus 2 is y squared at 5. Then let's expand it. So wy squared minus 2w is y squared at 5. Now we want y on its own, so let's get all the y parts together. So wy squared minus y squared is going to be 2w add 5. Then I want y, so let's factorize the y out. So let's get y squared of w minus 1 is 2w add 5. Therefore, y squared is 2w add 5 over w minus 1. Well, that's y squared. We want y. Well, how are we going to get rid of the squared? We're going to square root, aren't we? So therefore, y is going to be the square root of 2w add 5 over w minus 1. Now, you don't do plus or minus. I haven't checked the mark scheme, but they might allow it. I'm not sure. But in general, you don't need to do plus or minus here because you're not solving for y. We just want a general expression. When you're solving, yes, you do need to be particular with what values you have. But because we're just finding an expression or whatnot, we don't need to account for that here. But anyway, there we are. Okay, question 11. We got the equation of the two circles. We need to find the area of the shaded region, which is going to be here, right? Well, how are we going to do this? Well, I notice this essentially is a composition of two circles. Rather, I've shown it here. The big circle here, and then we have like a smaller circle inside of it, right? So I think the best step actually, and I noticed also this is a quarter of the circle, right? Of each circle. So I think the best strategy is to work out a quarter of each circle, the area of a quarter of each circle. So I'm going to call it the big circle and the little circle. So the area of big circle, that's going to be pi r squared, isn't it? But radius here. So what's the radius going to be? 0, O is the center. So distance here is going to be the radius. Okay, but the radius is here, isn't it? You should know in general, x squared and y squared is r squared. That's from normal GC. That is. So here 100 is r squared, so r is going to be 10, right? If you root 100. Likewise here, 36 is r squared, so r is going to be 6. So if you square root 36, you get 6. So the big circle, the radius of 10, so it's going to be 10 squared, which is going to be 100 pi. Okay, but then a quarter of area then, the big circle, well, it's going to be 100 divided by 4 pi, which is going to be 25 pi. Okay, and then we do the same for the little circle. So the area of the little circle, or the smaller circle, again, the radius of the smaller one is 6. Okay, so we've got the big circle again is here, and then the smaller circle's here. Okay, so the small circle will be pi lots of 6 squared. It's going to be 36 pi. And then we want the area of the quarter, right? Of area. It's going to be 36 divided by 4 pi, which is 9 pi. Okay, 36 divided by 4 is 9. Okay, so I've got the area of these quarter circles. But how are we going to get the area of the shaded region? Well, clearly the shaded region is going to be the area of the quarter of the big circle minus the area of the little circle. So you imagine it's like this. So the quarter of the area of the big circle's here, and then the quarter of the little circle is going to be here, right? So if we take these two away, we're left with this little region here. Okay. Cool. Okay, so then the shaded region or shaded area is going to be 25 pi minus 9 pi, which will be 16 pi, and that should be your answer. Cool. Question 12, expand and simplify. So again, this is just another exercise. They love testing this, but hopefully you should be able to do it. So again, let's work with this bracket first. So 2x cubed minus 9 of 3x squared of 4. Again, use FOIL or use whatever, but this is going to be 2x cubed times by 3x squared. Well, that's going to be to 6 x to the 5, isn't it? Because we're going to add the powers, right? X cubed times x squared would be x to the 5. Okay, then we're going to add 2x cubed times 4. That's going to be, hang on, let me do it up here then. So we know that's 6x to the 5. Then 4 times 2x cubed times 4 would be 8x cubed. Then we time minus 9 times 3x squared, that would be minus 27x squared. 3 times minus 9 is minus 27. Then we're going to do minus 9 times 4, which would be minus 36. Okay, cool. We can't simplify that anymore, so we leave it as that. Then I'm going to do this part here, x of x minus 4 squared. That's going to be x times of x minus 4, x minus 4. So again, if you're squaring it, the brackets repeat and the times by itself. So x, and then let's work out this expansion first. So it's going to be x squared minus 4x minus another 4x, which would be minus 8x, times positive 16. So minus 4 times minus 4 is positive 16. And then we expand it all with x, so it's going to be x cubed minus 8x squared, add 16x. Okay. So expanded this part and this part. Now we need to add them together. Okay. So we're going to have 6x to the 5 at 8x cubed minus 27x squared minus 36. Add x cubed minus 8x squared. Oh, that's x cubed. Well, sorry, not x squared. Minus 8x squared add 16x. So that's going to go to, well, then you just compare all the powers of x, right? So here, first of all, x to the 5, there's only one x to the 5, so it's 6x to the 5. Then we have x cubed, where we have 8x cubed, add another x cubed, that'd be plus 9x cubed. Then we have the x squared, minus 27x squared, minus 8. That's going to get us minus 35x squared, minus 27 minus 8, is minus 35. Then we have minus 36, but that's the only number here. And then we have this 16x at the end. And that, there it is. It doesn't matter how you order it. I could say 16x minus 36. It doesn't matter. But we can't do anything more of that. It just asks us to expand and simplify, okay? Not to factorize or anything else. There we are. Okay. Cool. Question 13. And that's a strategy if you get a nasty question like this. Do it part by part, you know? So expand this part first, then expand this part, and then you can add them together. Don't freak out over that, you know? Just split it and do it into manageable steps. Okay, question 13. So we are given y is a 12th x to the 4 and 3x squared at 4. Find the value of x for which this d squared by dx squared is 55. Okay, well you should recognise this is going to be the second derivative, not the first. So we need to differentiate twice. Okay. So how are we going to differentiate it once? Well, why is this? So again, dy dx. Well, this time it's written in a nice little polynomial form, clearly. So we can differentiate it straight off the bat. So dy dx, again, x to the 12th, x to the 4, for example. If we differentiate it, you're going to, again, times the power by the number in front. So it's going to be 4 over 12, x, and then we knock one off, so it's going to be cubed. 4 minus 1 is 3. Well, actually, we can simplify 4 over 12, can't we? Because 4 over 12 will go to a third. And then we differentiate the 3x squared. 3x squared will go to 2 times 3, which is 6. 6x, and then 2 minus 1 would just be 1, or just x on its own. And then plus 4, well, if you have any sort of constant, any number that's not tagged to an x, that always goes to 0. You can think of it because you could say every constant is like 4x to the 0. But you should know anything raised to the 0 is always 1. So this is saying 4 times 1, which is 1. Okay. Then if we apply the rule, then if you times the power in front by 4, 0 times 4 would be 0x to the minus 1. Right, 0 minus 1, knock 1 off. But 0 times anything is still 0. So we add a 0 here, but obviously adding 0 doesn't do anything, so we can leave it as that. Okay, cool. So that's the first derivative, but then we need the second one. So it's going to look like this: d squared y with dx squared, with the numbers in this order, but they give you this anyway. So yeah. So the second derivative, again, we're going to times the power in front. So you're going to left with 3 over 3 x to the 2. Knock 1 off. 3 minus 1 is 2. And then add 6x. So x has a hidden power of 1. So 1 times 6 is 6. And then 1 minus 1 is 0. So you knock 1 off. But x to the 0, as we just discussed, is 1. So that we just left with 6. And in general, when you have a linear term like this, ax, it will always just go to a, okay, because of this. So 6x will go to 6, for example. Okay, but we can simplify this because this goes to 3 over 3, so it's x squared, isn't it? Because 3 over 3 is 1. X squared is 6. Then we need to find the positive value for when this is equal to 55. So we need to equal this to 55. So then we solve this for x. Well, x squared then is going to be 55 minus 6, which is 49. Therefore, x then is going to be the plus or minus of the square root of 49, which is going to be plus or minus 7. Okay, root 49 is 7. But it asks for the positive. Okay, so x is going to be positive 7. There we are. Cool. Question 14 now. The nth term of a sequence is 3n squared over n squared add 2. One term of the sequence is 32 over 11. Find the value of n. So one term, so this is the general term, right? We need to equate this to 32 over 11, right? To find the value of n in that, what the term is, you know. So we're just solving some sort of algebraic fraction here. So we can cross multiply to say 32 lots of n squared add 2. It's going to be 11 lots of 3n squared. Then let's expand it. So then 32n squared add 32 times 2 would be 64, would be equal to 33n squared. 11 times 3, 33. Then I can get rid of 32n squared both sides. So you're left with 33n squared minus 32n squared is just n squared. And that's going to equal 64. But then n, again, it's going to be like plus or minus root 64, which is plus or minus 8, because root 64 is 8. Okay. But which one we're going to take? Well, nth term, n is always positive, right? Because you can't have a negative position. Because obviously it always starts from the first term. N is 1, 2, 3, 4. You know, that's where it starts from. So n always is positive with an nth term, okay? So n positive, so n is equal to 8, okay? Cool. Then it says, write down the limiting value of the sequence as n tends to infinity. Okay. So it says write down, so I believe we probably just need to know how to spot something like this. But in general, when you have any fraction like this, an algebraic sort of fraction with n or x or whatever, here, and you have like n's on the top and the bottom, and you need to see what happens when n goes to infinity. So that n becomes really, really large. There are two ways to do because you've got a calculator as well. What you could do, for example, is substitute a really, really, really big number for n. Okay, because that would mean n is infinity almost. So you could say n, for example, would be like 10 to the 30. Because obviously that's going to be one with like 30 zeros, which is going to be a massive number. So then, the nth term, with that in mind, is going to be 3 lots of 10 to the 30 squared over 10 lots of 30 all squared, add 2. If you plug that in, 3 lots of 10 to the 30 squared over 10 lots to the 30 squared, add 2, you get 3. Okay, this will actually simplify to 3. Okay, and that tells you the limiting sequence. However, and in general, this actually came from a non-calculated paper, so that isn't, the method. But because you got a calculator anyway for paper 2, you could do it like that. But if they ask you what you need to spot, particularly with fractions like this, um, you need to spot that the highest power, so we've got an n squared, the highest power, or the called the leading coefficient, so that the highest powers essentially needs to go to 3n squared over n squared only. The plus 2 is irrelevant. Hang on a second. Uh, and actually, this will then lead to cancellation. Where's my pen? Why don't I have a pen? Where's my pen? Hang on a second. Found it. There we are. But this will lead to cancellation, right? Because the n squareds will cancel out to be left with just 3. Which is how we get that more formally. Alternatively, another way of visualizing this, I think this is the far better way of doing it. What you could do is you could kind of change this fraction a little bit by times it or dividing by 1 over n squared, right, to both sides. So you divide the top and bottom by n squared, to be left with, well, 3n squared over n squared be left with 3. Um, n squared over n squared be 1. And then 2 will just be 2 over n squared. And what you will notice is when you have a number in general, 1 over n, when that number goes to infinity or big number, you're divided by a big number. So you can try that with your calculator. Divide 1 divided by a big number, it will tend to infinity. Okay. No, sorry, 10 to 0. Sorry. If you do 1 divided by a big number, will go to 0. Okay. And so actually, we can substitute whenever we have some multiple 1 over n, this will go to 0. So again, you'll be left with 3 over 1 at 0, which would be 3 over 1, which should just be 3. Again, that's another way you can get to 3. Okay, but for Jesus' sake, just spot. You just need to spot the coefficients and the highest power coefficients. Um, and then and then that'll go to 3n squared over n squared. The n squared will cancel, be left with 3. Okay, and that would be your limiting value. Another example, I guess, say if we had 4x and 6 over 3x minus 2. And then we want to see what happens at x goes to infinity. But again, the same sort of reason. We've got the highest power of x, which is just going to be x, right? X to the 1. So ignore all this, so we'll be left with 4x over 3x. And so we can cancel the x out to be 4 over 3. So the limiting value here would be 4 over 3. Okay, so that's generally what you want to do in these sort of questions. It's only one mark. Another one that I've seen that might come up. I did spot this on the past paper. I thought it was asked before. You could alternatively be asked for a sequence like this, sort of an plus 1 is 6 minus 2an. Okay, and obviously it's like a recurring sequence. And you ask for the limiting value. Well, the limiting value in this case, if you ever ask something like this, you need to recognize that obviously it goes to a limit L, so it goes to some number L, and when it goes to L, think about it. For long term, it's not going to go away. For example, say a sequence looks like this. Let's go here. It's going to level off like this, isn't it? And it's going to go to this number L. So actually, when you have enough terms, they become the same. Really, there's no difference between them. So that would mean an plus 1 equals an, which again is going to be this limit L. So then you want to find the limiting value. You essentially make both of these terms the same. So that means L is going to be 6 minus 2L. That means then 3L will be 6, L is 2, and that'll be the limiting sequence. That's telling you the sequence again will converge to this number 2 here. Okay, I'm just trying to cover all bases there. But if they ask for limiting values, so those are the two you need to consider. Okay, ones with fractions like this and they cancel out the highest power, or when you're given a recurrence sequence like this, you need to set the two terms equal to each other. And there we are. Okay, cool. Okay. Okay, I need to switch to the other set of questions. Okay, here we are. Okay, now it's asking to work out the gradient of the curve at the point when x is minus 1. So gradient, when you're not really given any points, in general, a gradient is going to be the derivative, okay? That's the same thing, the derivative. So we need to compute the derivative or differentiate y here. But the problem is, again, it's not a nice polynomial because we're divided by this 4x squared here. How are we going to do that? Well, I can recognise, because we've got a fraction, we can split this up term by term. So we can say it's 12x cubed over 4x squared. So that's y. Minus 8x over 4x squared plus 3 over 4x squared, right? Hopefully you recognise split this up because it's a fraction, okay? I'll just split the numerators up, and now I can cancel this part by term by term. So 12x cubed over 4x squared, well, 12 divided by 4 is 3. X cubed over x squared will go to x to the 1, because you subtract 3 by 2, which is x. Let's deal with the second bit then. So minus 8 over 4 will be 2. X over x squared, now that will be x to the minus 1, because then this is 1. 1 minus 2 is minus 1. Now don't be afraid you've got a negative here, that's completely fine. That's what you want, because then we can still apply the same rule when you differentiate. Okay, and then 3 over 4 over x squared. Okay, well, again, this is sort of like x to the 0, isn't it? So then x to the 0 minus 2 be left with x to the minus 2. And that'd be 3 over 4, okay? Because this is 3 over 4. And alternatively, you could realise 3 over 4 x squared. That's the same as saying x squared. If you divide them, it's a reciprocal, isn't it? So x to the minus 2 is the same as 1 over x squared, which is what we've got here. So this same as 3 over 4 times by x to the minus 2, which is what we've got here. Okay. But I think that's probably the tricky part of this question is converting to this. Hopefully you can wrap your head around that. Okay, that's a very tricky term to deal with there. But hopefully you can realise how we got from here to here. Um, but yeah. Okay, I'm gonna leave that there. Okay, so now we've got the. Now it does look like a polynomial. I know we've got some minus powers, but we can apply the same principle because then if we differentiate dy dx, again 3x, so that's 3x to the 1 times by 1 by 3, you get 3, and then you knock 1 off. X is 0, but x is 0 is 1, so 3 times 1 is just 3. And again, with a term like this, it's always just going to be 3. Okay. Okay, so that's 3. Then okay, and minus 2. So what's going to go here? So let's do it separately. 2x to the minus 1. If we differentiate, again, we times the power by the number in front. So it's going to be minus 2 times minus 1. That's going to be positive 2. Okay. And then x, and then you minus 1, you knock 1 off. And minus 1 times add minus 1 would be a minus 2. That is your derivative there. So that'll go to plus 2 x to the minus 2, okay? In the same way, 3 over 4 x to the minus 2, again, you times minus 2 by 3 over 4, that'll be minus 6 over 4 x, and then minus 2 and knock 1 off would be minus 3. Okay, minus 2 minus 1 is minus 3. So minus 6 over 4, but 6 over 4 is 3 over 2, isn't it? So that will go to minus 3 over 2 x to the minus 3. Okay, and that's your derivative. Okay, now that is the grade. That's a general gradient function, and that's why this is so good, differentiation. That's the whole point of differentiation. Instead of approximating by drawing tangents to curves and finding their gradient, and because the tangent only works at one particular point, this derivative expression gives us a general expression for all points on the curve without having to draw any tangents and stuff like that. And it gives us the actual answer, not an estimate, by estimating a gradient on the curve. You know what I mean? That's why we do this. The whole point of this is to get a general gradient expression. And the whole idea then is we can just substitute points in quite nicely, and that will give you the gradient at all of these points. So then I'm going to sub in x is minus 1. Then the derivative dy dx is going to be 3 at 2 lots of minus 1 minus 2 minus 3 over 2 minus 1 minus 3. And that's going to get, I'm going to get rid of this bit now, not make it cluttered. Then you can put that to the calculator. So that's going to be 3 add 2 lots of minus 1 to the minus 2. Minus 3 over 2 minus 1 to the minus 3. And that'll get you 13 over 2. And that's your derivative, that's your gradient. There we are. Cool. And see, that's the beauty of it. We can get an accurate, actual answer 13 over 2. Rather than just try and plot this curve. And some curves are really, really, really hard to plot. Like trying to plot this curve, for example, would be a nightmare probably. And then you have to draw tangents, and you have to estimate it's a whole mess. Here it's a lot more cleaner, and that's the whole point of differentiation. But yeah, the central idea you need to recognize is differentiation correlates to the gradient, okay, or the rate of change, because obviously the gradient is essentially the change in y, the change in x, right? So yeah. Okay, question 16. More transformations on matrices. Describe geometrically the transformation represented by A. Okay, so again, we're applying a transformation. So let's again consider this sort of unit square we got. How the best way to do this? Again, you probably might be able to memorize them. You might be able to just state what the matrix represents. But if you weren't going to do that, like I haven't learned, I don't know what they are. What you can do is sort of derive them. Again, it's unit square. So consider all the vertices. So this is going to be obviously 0, 0 here. That's going to be 1, 0. That's going to be 1, 1. That's going to be 0, 1. Okay. And so what this matrix is doing is saying 1, 0, 0 minus 1. Hang on a second. Okay, so remember, it's going back to what I was talking about earlier. In general, the transformation. So you have a general point x, y, and you're transforming it. So you're going to multiply by this matrix, and you're going to get out the transformed points here. Okay, but so let's work this out. So again, this point, this time we're only going to get a 2 by 1, so 2 rows and 1 column. Okay. So let's work this multiplication out. So that's going to be 1 times x, which is x, times 0 add y, which is 0. And then 0 times x and minus 1 times y will be minus y. That's telling you, if you have a point x, y, we want to then keep the same x coordinate, but then y, we make it negative. Okay, if that makes any sense. So, for example, the origin, well, 0, 0 will still be 0, 0. That's cool. Then 0, 1 here. 0, 1, again, 0, 1 would go to, if we're using this sort of formula, x will stay the same, 0, then y will be minus y, so it'd be minus 1. So 0, it'd be here, right? Cool. Likewise, this point here, 1, 1. Again, the x stays the same, so 1, then y would be negative, so minus 1. That would be down here, right? And you could probably spot then that this point here will remain the same. And you can see that here, because 1, 0, the x stays the same, 1, and then 0 minus 0 is still 0. So that is our reflection square here, okay? And yes, so what can you see happening here? Well, it's going to be a reflection, isn't it? Clearly, there's actually two possibilities if you just look at the diagram. It could be a reflection or a rotation 90 degrees clockwise. Well, which one can we rule out? Well, this is where you need to consider what the points go to, not the shape in general. You can have the shape be the same if it's rotated or reflected, but the points themselves, they only undergo single transformation. Let's have a look. So 101. Remember, this went down to here. So here it went to here. If you then reflect, but if you instead rotate the same point 90 degrees, it would go to here, wouldn't it? Not here. So the only way you can go from this point here to this point here is a reflection in the x-axis, isn't it? So that's going to be our answer. Reflection in x-axis. Cool. Okay, it's a very messy diagram. That's the sort of method, right? Again, so consider the unit square, consider what all the points would go to, and then you can use that to aid you. Then it said we're given a matrix B, and we need to represent what B squared does. Well, first of all, we're going to need to compute B squared, isn't it? So again, like with a normal number, squaring it, you times by itself. So b times b is going to be 0, 1, and minus 1, 0. 0, 1, and minus 1, 0. And that's going to go to this here. There we are. Let's make this a bit. Oh, where's my pen gone? Oh, there it is. Here. Okay, so again, it's going to be a 2 by 2, so it's going to be 4 entries. So again, matrix multiplication. This is row 1, column 1. So we want the first row times by the first column to second. So that's going to be 0 times 0, which is 0. Add 1 times minus 1, which should be minus 1. And then we want this one here. So it's going to be the first row, the second column. So the first row again here by the second column. So it's going to be 0 times 1, which is 0. And then 1 times 0 is 0. Cool. Okay. Now, again, I want this entry here. So it's going to be, again, the second row and the first column this time. So we want the second row of the first matrix by the first column. Here, the second one. So minus 1 times 0 is 0, and then 0 times minus 1 is still 0. And then again, we want this last bit here. So it's going to be row 2, column 2. So we want the second row of the first one and the second column of the second. So minus 1 times 1 is minus 1. 0 times 0 is 0, so it's just minus 1. Okay. And that's our matrix. So b squared is minus 1, 0, 0, minus 1. Now we need to work out what happens here. And again, you might be able to spot what's you might spot what matrix it represents. But let's consider the unit square again. So again, let's draw a little square diagram here. And then we want to work out what each happens at each point. And again, let's consider minus 1. If we times it by x, y in general, what if we do this product, it's going to be minus x and then a minus y. So essentially what's happening is with each coordinate x, y, we take the negative of it. So for example here, well 0, 0 first of all here, will stay 0, 0. Then x, y, well here, this is 0, 1. So that's going to go to 0, minus 1. Okay. So that's going to be down here. What about this point then? This point is 1, 1. So that's going to go to minus 1, minus 1. So it's going to be down here, isn't it? Okay. Hopefully you can spot how we got from here to here. You know, there's only one way we can kind of do that. Well, there are two ways actually, but hopefully you can spot. Anyway, and then this last point here, it's going to be 1, 0. That's going to go to minus 1, 0. So it's going to be here. And then as squares, we're going to run this. And hopefully you recognise, well, what's that going to be? It's going to be a reflection, a rotation, 180 degrees, isn't it? Right, it could be, and then it could be clockwise or anti-clockwise because they're the same. 180, it's the same thing, isn't it? Rotation 100 degrees. I'll just say clockwise. It doesn't really matter. And we need a point of rotation, don't we? And it's always going to be the origin, which is 0, 0. There we are. I said earlier there was another one. You might think it might be reflection in the line y is minus x here, because this point here goes to here, and that is the reflection. Same with this point here. This point here goes to this point here. Ooh, as was this point here. Oh God. This point here will also go to here. But you can rule it out. I'm pretty sure you can rule it out. Oh, no, no, no. Oh, no, no, because the points don't correspond. So here, 1, 1. Hang on, I think. 1, 1 would go to 1 minus 1. No, minus 1 here. Okay. Then here, 1, 0 would go to minus 1, 0. Ah, there we are. So if you consider this point in particular here, you could, again, you might think by inspection it could be also reflection in y is minus x. But then again, consider the points in turn. So this point, for example, this point here, let me draw it again. That's 1, 0. If we use this formula, it's going to go to minus 1, 0 here. Okay. But that's not reflection the line y is minus x, because if we reflect it, it would be here instead. But the point is here. So therefore it rules out the fact it isn't reflection in y minus x. So therefore the only other way it would be a rotation 180 degrees. Okay. Alternatively, you could spot, well, actually, minus 1, 0, 0, minus 1 is minus of 1, 0, 0, 1. So it's kind of like pulling out scale factor of minus 1. But if you're doing a scale factor of minus 1, say for this in general, uh, that's the same as rotating it 180 degrees, because if the center of enlargement is at 0, 0, again, you're kind of just reflecting it, no, rotating 180 degrees. And then that'd be here, that'd be there. And then here would go to here. And yeah, so it would alternatively be a scale factor minus 1. But I think it's a lot easier to recognise it's a rotation of 180 degrees, okay? They're the same thing. You could either rotation 180 degrees about 0, 0, or a scale factor of negative 1, or technically an enlargement, but you know, it's a scale factor of minus 1 about the 0, 0. But yeah, so that's the thing you need to be able of. You need, if you, again, what I did here, and in the other question as well, but you might have two possible transformations. The square might look the same under both two different transformations, but to rule one out, again, you need to consider what each point maps to. So, for example, again, to reiterate, this point here on the square here, actually, minus x, so that's 1, 0. Minus x is minus 1, and then y 0, it would go here. If you were to reflect it in the line minus x, which you might look from looking at this diagram here, it might be a reflection in minus x. It would actually go here instead. But that's not what we want. We want it to be here, so therefore it cannot be reflection. So therefore the only way is a rotation. Hopefully it made sense. This is quite a hard, very hard topic in my opinion. So you know what? It might, maybe you might, if you do struggle, you might find some benefit of just memorizing them. It's up to you. Um, because you should be able to spot this with rotation 180 degrees if you were to memorize it. Well, the B squared matrix anyway. But yeah, that's how you sort of derive it anyway. By looking at how the unit square transforms, but in particular how the points transform on the vertex of the square. Okay, question 17. Simplify fully this. So actually, I recognise, first of all, again, let's split this, do all these bits separately. So firstly, x over 2 plus 3x over 5. Well, I recognise we're just adding x's. So this is the same as a half of x, add 3 over 5x, right? And then I'm just adding a half, add 3 over 5. So half, so I'm going to bear that in mind. So a half, add 3 over 5. Again, you have a calculator for this, but that would go to 5 over 5. No, sorry, 5 over 10 add 6 over 10. So have a common factor of 10, denominator of 10, and that would go to 11 over 10. But if you did that on the calculator, you just immediately, you'd get 11 over 10 straight away, but that's kind of how you work it out. So that's going to be 11 over 10x, okay? Because we like collected like terms, if you will. So we simplified the left bit. Now, what about the right-hand side? I'm going to do it over here. So then root x to the 6 over 4, that's what we've got. Okay, well, notice we can use index laws. And the first one is actually, we can split the square root to both the top and the bottom separately. So it's going to be root x to the 6 over root 4. That is the normal GCSE third law, okay? That shouldn't be too unsurprising. So that'll go to, well, x to the 6. Well, then, x to the 6, well, a square root is a half, isn't it? Again, that's another third law. Okay, we can rewrite a third as a to the half, okay? That's over root 4, which is 2. Okay, then x to the 6 of a half, again, we have a bracket. 6 times a half is going to be 3, okay? And now we've got, and then that's simplified. And so actually, this then is saying this left-hand bit is 11 over 10 divided by this bit, which is x cubed over 2, okay? And then if we put, we can put the x on top if we wanted to. Because now we have two fractions. And so if we divide, that's KFC, isn't it? So you keep the first fraction, and then you type, so you've changed the sign, and then you flip the second fraction. So it's going to be 2 over x cubed. And now when you time to do fractions, you just times the top and the bottom separately. So 11x times 2 is 22x. 11 times 2 is 22. Then 10 times x cubed is just 10x cubed. And then we can simplify this. So firstly, 22 over 10. If you put that in your calculator, it's going to be 11 over 5. And then, or you could convert that to a decimal if you weren't comfortable. You could say that's 2.2. Okay. And then x over x cubed. So that's again a hidden power of 1. So then you say 1 x to the 1 divided by x cubed. Again, you subtract the powers by index laws. So 1 minus 3 is minus 2. Okay. So that's your final answer if you wanted to. Or the other way with fractions, this would be 11 over 5x squared or 11 over 5x to the minus 2, whatever you prefer. Okay, but I imagine some people might struggle with the fraction bit with the simplifying. You could do it like this. I'm going to double check. This should accept that, the decimal, but to make sure not spread anything wrong, I guess. The mark scheme. I'm going to double check the answer. So this was page June 2022, paper 2. They should accept the decimal version, I think. I don't know. It didn't say to leave it as a decimal, it just says simplify. That's simplified fully. Uh, uh, yeah, they allow 2.2x to the minus 2. Okay, cool. Fractional decimal equivalent. Complete. They accept all three of these forms of answers. Cool. Okay. Question 18. The point P on the curve, again, this y looks like a nice polynomial, so that's fine. P is the point where x is 2. The grade at the normal is the minus a quarter. Okay, so firstly, like I said earlier, the gradient is always linked to the derivative, so we're going to need to differentiate. So if y is ax cubed and 10x squared, again, don't freak out about the a. Okay, that's an a, not a 9. There we are. Don't freak out. We'd still apply the same rule that we know. So then the dy dx. Again, you're gonna if you have a power of 3, so it's gonna be 3 times a, which is 3a. x, and then knock 1 off, so squared. And then 10, again, 2 times 10, times the power by the number in front, that'd be 20x of 2 minus 1, which should just be 1, which should just be x, right? That's our derivative. So that's a general gradient. We need it at x is 2. So at x is 2, dy dx then is going to be 3a lots of 2 squared, 20 of 2. So 2 squared is 4, and then 4 times 3 is 12a, and then 20 times 2 is 40. Okay, cool. So that's the gradient at x is 2, obviously with an a, but that's just a number, right? Okay, then it says the grade the normal at p is minus a quarter. Obviously, them underline normal, they made it bold. So what this gradient is, like I said earlier, is estimating the gradient of the tangent at the point, say here, I don't know. That gradient that we substituted in at x is 2, say 2 is here at this point, P. That's the gradient that's the gradient expression, okay? That's the gradient of the tangent. If you draw a tangent at the point, obviously the tangent, when we draw it, gives us an estimate of the gradient at the point. What the normal is saying is it's perpendicular to the tangent. Okay, so that's a tangent. This is the normal, and they're perpendicular. That's the whole point of a normal. Okay, is to be perpendicular to the tangent. And so essentially, the gradient of the normal and the tangent are perpendicular, right? So how do we work with a gradient of two perpendicular lines? Well, you take the negative reciprocal of one another. So, so we could take a negative reciprocal of this, or I think the best way is to take a negative reciprocal of this instead. So, perpendicular gradient of minus a quarter. Well, that's going to be the negative reciprocal. So, negative of a negative is a positive, and then we take the reciprocal, so it's going to be just positive 4, isn't it? Because you flip the fraction, so it'd be 4 over 1, which is just 4. So if the perpendicular of the normal, that's the tangent gradient, okay? So the normal is minus a quarter, so then 4 is the gradient of the tangent. But this is the gradient of the tangent. We worked out that's the whole point of the derivative, remember? So that'll be equal to 4. But then we can solve this for a, so that means 12 of a is going to be minus 36. 4 minus 40 is minus 36. That means A is going to be minus 3, isn't it? 36 divided by 12 is 3. So make it negative. Cool. Okay. Question 19. Then we're asked to solve this equation here with some nasty indices. Okay, but again, we have a bracket. Let's expand this out. So we're going to have x to the half minus x to the 3 over 2. That's squared, so that's again times by itself. And then we can expand it. Again, use FOIL or whatever, but this is going to be x to the half times by x to the half, firstly, right? If you do this, oh, if you do this sort of thing there, well, then if you times into numbers like this together, you add the powers. So half add a half is just 1. Okay, so you're left with x. Then we're going to do x to the half times by x minus x to the 3 over 2. So again, that's going to be a half add 3 over 2, which is going to be 4 over 2, which is going to be 2, right? So it's going to be minus x to the 2. Y minus, because there are a minus here. And with times, oh, sorry, no, sorry. Here is times by this, and this has a negative. So we have to make it a negative, okay? So that's negative x squared if you times x to the half with minus x to the 3 over 2. And then we do the same here. So x to the minus 3 over 2 of x to the half. Again, it's going to be another negative x squared. Again, 3 over 2 add a half is 4 over 2, which is 2. and then make a negative. And then we do the same with the last bit here. X minus x to the 3 over 2 times by minus x to the 3 over 2. So firstly, it's a positive because a negative times a negative is a positive. So bear that in mind. But also 3 over 2, then add 3 over 2. That's going to be 6 over 2, which is 3. So that's left with positive x to the 3. Again, positive because we have times the two negatives. And that's our expansion. And actually, it's a lot nicer to work with. And so this is all equal to x squared at x, which is again given to us. And then we just need to simplify. So I want to make this equal to 0 to solve it, probably. So let's get rid of the. Let's simplify this bit first of all. So this is x minus 2x squared as x cubed is x squared at x. So then I'm going to say, well, I'm going to move the x squared to the here to the left. So x minus 3x squared at x cubed, and then we're going to move the x there as well. But then we're going to have x minus x. That will get rid of this, as you can see. There we are. So then we're left with this, and this will equal 0 now because we moved everything to the left side. Okay, well then I can say well then I can factor out an x squared term, can't I, to solve it? So it's going to be x squared of x minus 3 equals 0. Hopefully you can see that. So we factorise an x squared out, and then we solve it. So that means x equals 0 because x squared is 0. So then that means x has to be 0, or x is simply 3. So those are our two solutions, 0 and 3. Cool. Question 20 now, not a lot long to go. We are given the graph of y is x squared minus 6x at 5. By drawing a suitable linear graph, so we need to draw a line here somewhere as well. Find the solution to this. Now, what you need to notice is this is not the same expression here. But what we can do is sort of, let's start with this, x squared minus 6x at 5. Then we need to get to minus 7x, x squared minus 7x at 9. Well, the x squared is the same, that's cool. But we need to go from minus 6x to minus 7x. So that means so that's equals 0. Okay. Well, we're going to need to minus another x, don't we, to get from minus 6 to minus 7x. In the same way, to get from positive 5 to positive 9, we need to add another 4. And that's all equals to 0. Okay. Okay, but then again, I want to keep this original part the same. So x squared minus 6x plus 5. And then I'm going to move the other parts to the right. So it'll be x minus 4. And actually, this, you should recognise, is a straight line, right? It's a straight line with gradient 1 and y-intercept minus 4. So it's going to look a bit like this, isn't it? These are not simultaneous equations. These lots say y is x squared minus 6x plus 5 and y is x minus 4. So when they equate to each other, that's when they intersect. So that's the solution. Okay. And that's a solution to this equation as well, when they both intersect these two parts, you know. So we've already got this graph, this this quadratic part here, but we need to add this line x minus 4 here. So we need to draw it, okay? So that's gonna obviously it passes at minus 4, 0. That's the y-intercept here. So the y-intercept is minus 4, 0. So it's going to pass here first of all, isn't it? But we need another point to then connect to draw a line. Where does it intersect the x-axis then? So if we substitute x is y0, well then 0 is x minus 4, so then x is 4. So it also will pass through 4, 0, okay? And then that's our line. If we connect these 2 points, that will give us a line. Oh god. Like this, obviously with a ruler, but I don't have a ruler with me. It's a bit, something like that. Okay, something like that, but with a ruler, it needs to be very nice. nicely drawn. Okay, well then, when they like I said, they equal to each other when they intersect, which should give the solution to this. Where do they intersect? Well, it's going to be here and here, isn't it? So then the x values is going to be, and then we're going to read off the graph. Okay, so if we read off the graph, it's going to be this point here, which is going to be 1.8. Hopefully you can see that, roughly thereabouts. And here, it's going to be, oh God, I might have to zoom in for this. Hang on. There we are. And here, it's going to be about, it's going to be like in the middle here, isn't it? So this is going to be 5.2 and that's 5.4. So in the middle is going to be 5.3, isn't it? Okay. Uh, Again, hopefully you can see that right. This intersection here is 5.3 in the middle between these two boxes here. So that's our solution. Okay, if you read off the graph, let's get back to normal then. Oh God, go back. Hang on. There we are. So we saw that when they intersect, the solutions are 1.8 and 5.3. Okay. Obviously, with a ruler, it might be. I'm probably going to be off by like a decimal point because I sketched it uh, without a ruler, but you should use a ruler there. But yeah, let me just check the values you can get here. Um, uh, so you either five, so they get 5.3, which is what I've got, cool, and 1.7. Yeah, that comes on my without a ruler. They set between 1.6 and 1.8, cool, and between 5.2 and yeah. So I would have been right anyway, but yeah, they set some leniency, but yeah, that's what you want to do there, cool. Okay, question 21. Solve these simultaneous equations. There are a lot of different methods for solving stuff like this, a lot. But for GCSE, what you really expected to do essentially is, well, you could either substitute one equation to the other. So you could say x is 2 minus 3z. Then you substitute x here to then say 2 lots of 3 minus 3z and 1 plus y is 13. You know, I'm going to do that here then. So then I'm going to say x is 2 minus 3z. So I'm going to then I'm going to say sub x into 2x add y is 13. But therefore 2 lots of 2 minus 3z plus y is 13. So that if we expand, that's going to be 4 minus 6z and y is 13. But I want all the x's, y's, and z's on the left and put all the numbers to the right. So it's going to be minus 6z add y is going to be 9. Okay, not 13 take away 4 is 9. Okay, but we also have this equation on the bottom. We also have this one here of z minus 2y is minus 7. Now, actually, this is a simultaneous equation at this point that you should all know and love. Okay, it's a simple two simultaneous equations that you should know how to solve with normal maths. Okay, how are we going to solve it then? Well, again, the two main ways you can either eliminate or substitute. Well, I've already substituted, so I might as well substitute again. So I'm going to say y is 9 add 6z. So I'm going to say sub y into z minus 2y is minus 7, the second equation. Therefore, z minus 2 of 9 add, that should be 6. 6z equals minus 7. So that means z minus 18. 2 times 9 is 18. Minus 12z is minus 7. So that means minus 11z is going to equal positive 18 add 7. That's going to be 11, right? Well, then, therefore, you can see that, therefore, z is just going to be minus 1, right? Divide by minus 11. 11 over minus 11 is minus 1. But you found your z, so then, therefore, if I do it here, y was 9 add 6z, wasn't it? So it's going to be 9 add 6 of minus 1. Well, that's going to be 9 minus 6, which is just going to be 3. Okay. And then therefore we can find x as well, because then x, remember, we said all the way up here, x is then 2 minus 3z, which is going to be 2 minus 3 of minus 1. So that's going to be 2, minus 3 times minus 1 is positive 3. So it's going to be 2 add 3, which is 5. So therefore x is 5, y is, what was it, 3, and z is minus 1 is a solution here, if you substitute it in like that. Alternatively, it's probably a method that probably a lot of people have been taught. Alternatively, with simultaneous equations, if you don't want to substitute, sometimes you can eliminate variables. So I think the strategy you probably learned is to eliminate one variable from the equations to then get a two like this, so like a two variable simultaneous equation which you can solve. How are we going to do that? Well, let's just say I don't know. What should we pick to eliminate? X, Y, or Z? Uh, let's just pick Z. X. X is the first one. Okay. So if we're going to eliminate X, well, how are we going to do that? Well, we're going to have what we have two equations with X in. So we're going to say 2x add y is 13 and x add 3z is 2. So if we're gonna eliminate x, I'm gonna need both equations have the same coefficient of x in. So this is gonna have to be times in by 2 to be left with 2x add 6z is 4. Then I can subtract that with the first equation here with minus 2x add y is equal to 13. So then if we do that, well then 2x minus 2x is 0, which is what we want. Then 6z minus y is going to equal 4 minus 13, which is minus 9. Okay, and actually that's the equation we've got here, except it's the other way around because it's times by minus 1. Because then if we times this by minus 1, we get minus 6z add y is positive 9, which is what we got here. And then you can compare it with the third equation here. So once you eliminate x from from all the equations, so there's no x's anymore, then you just got two variables and you should have two equations. If I'm completely honest, though, I do think substitution is a lot easier, especially when you get more complicated simultaneous equations. So say, for example, we had, you might see this comment 3a, for example, a 2b at 7c is equal to blah, 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 like 8. Then like 5a at 4, no, then 5b minus 2c is like equal to 15. Then you're going to have like 11a at 13b, I don't know, then add 5c is equal to 21. These are very, very nasty ways of it's very nasty to try and eliminate a particular variable because they're all very awkward. You have to, and if you eliminated, say for example, say if we picked the first two equations like we did to eliminate, say a, that's the first one. There's still an a in the third equation, so then you have to get rid of a from the third one, which you've done the first and second, and it's an absolute nightmare. I do much prefer substitution because then you could say, well, take the second equation, well, the second equation, then 2b would be like 8 minus 3a minus 7c. Okay, but then you have to divide by 2. You might get a bit of a fraction, but you're going to get a fraction either way, if you eliminate it or not. But then you can substitute b quite nicely into the other two equations, the second and the third one, and then you can get rid of b quite quickly. And then you got it in terms of a and c, which then you can solve that way. I much prefer substitution. Obviously, do it however you've been taught or whatever, how you learnt it. But I do prefer to just rearrange one equation to then, say, for example, x is 2 minus 3z. And then you can substitute it to the other two equations. And then you got a two. Then you only got two equations with two variables, without trying to like manipulate it to try and eliminate all the different equations. I don't know. It all depends on however you want to do it, really. But there we are. Cool. Okay. Uh, question 22. So then it's asked us to write this in the form. So a pretty common one, really. You just need to complete the square, which is actually a normal GCSE maths technique. But here it's a bit awkward because we've got a number of 6 in front of the x squared. Wow, how are we going to deal with that? Well, just factor 6 out. And then it just becomes a single x squared. So it's going to be minus x squared minus 24 divided by 6 is minus 4x. And then 17 over 6. Well, 17 divided by 6 isn't a nice fraction. So we just leave it as that. Because then if you divide each part, everything inside here by 6, well then if you times by 6 afterwards, you get the original quadratic back. Okay. Why are we doing this? Well, it makes it a lot easier to complete the square. Okay. Because then we can complete the square in this middle bit here. So again, that's going to be 6 lots of, and then we can complete the square. So it's going to be x minus 2 all squared. And then we're going to minus the square of that. That's going to be always minus, by the way. Minus 4, add 17 over 6. And then we can simplify it in the bracket a little bit. So that's going to be 6 lots of x minus 2 squared. 17 over 6 minus 4 is actually minus 7 over 6. Okay, if you just compute that. Again, if you were without a calculator, well, 17 over 6 minus 4, well, that's minus 4 over 1, really. That's still a fraction. And then a common denominator of 6, right? 17 over 6 minus 4 times 6, which is 24 over 6. That will get you minus 7 over 6, which is what we got here. But you, with a calculator, you can just put it in the calculator. I say that because this was on a paper 1, but they can easily ask you to do it on paper 2 as well. Okay, that's fully simplified. Now let's just bring the 6 back in. So let's times it all by 6. Let's do 6 lots of x minus 2 squared. Minus 7 over 6 times 6 is just minus 7. And there we are. We've got it in this form here. That everything's an integer. Cool. So that's just complete the square. Okay. Make sure you know how to do that. Okay, question 23. I need to charge my laptop. Nearly there, though. I've got like 3 more questions, I think. But these are the harder ones, I think. And it depends how, I don't know. But we are given a cos graph, cos of x. And we are told that when cos x is minus k here, we get the solution alpha. Then it says to find where the 2 boxes to find the other values of x, or the other solutions to cos x is minus k. So when cos x is minus k, if we were to continue this on, obviously we've got a solution here, which is alpha. But then we get another solution here. How would we get this one? Okay, so then if I just get rid of this. So we have a solution here and a solution about here, right? If you continue the line on. Well, the key thing to note with these trig graphs like this is that they're symmetrical about their humps, right? They're symmetrical about the dips like this. So this is like the maximum, the minimum point here. So everything on the left is equal to everything on the right, okay? thereabouts. It's symmetrical about this has a line of symmetry about its like its hump. Okay, so we're going to utilize that. Well, what that means is the difference between 0 here, x is 0 and x is alpha, the difference is alpha here, right? The same difference here has to be, therefore the next solution has to be between 360 and then alpha here, okay? So 360 and then this solution here. So again, if this is between 0 and alpha, again, because it's symmetrical here, the other solution is going to be from 360 to this solution here, and the difference is going to be alpha. Okay, so if we want this solution, well, we're going to have to take 360 away from alpha, aren't we? Okay, because clearly 360 minus alpha, and then we add an alpha on, we get to 360. So if it's symmetrical here, when it's symmetrical between 0 and 360 at either end. Okay, but you just need to visualize that. And so then, if we were to continue this on here, that's saying that this solution is 360 minus alpha. Okay, hopefully you can see that by noting that the difference between the two solutions, between 0 and alpha here, and 360, and then the next solution, the difference will always be alpha. Okay, there we are. So that's naturally you should notice if you scroll down, this is one solution here, but that's for two boxes. So then what would the other solution be in terms of alpha? Well, those are the two solutions. We get rid of all this mess now. Those are the two solutions here. Um, but we should know the cos graph. There are infinite solutions because of the fact it repeats itself. If we were to continue this graph on like this, well then if we draw it here, the next solution would be here. But it repeats every 360 degrees. So actually, if we add 360 on to alpha, we get the next solution. And then if we added a 360 onto here, we would then get the next solution for that as well. But those are two answers, okay? And that's in general how you solve a cos graph. So if cos x is some number, k or minus k, that's how you can get it, okay? But yeah, there we are. Then it says for part B, then it says circle an expression for x. So the solution with sine x is minus k. Okay. Well, here we have a cos. So now we need a sine. So the best thing to consider probably is to draw a sine graph, right? Um, so let's get rid of this. Let's get rid of all this waffle. Um, so then we consider the sine graph. So a sine graph is going to look like this, isn't it? Between 0 and 360. So when we have minus k here, again, minus k will be about here, right? If we continue that on, it would be about there, wouldn't it? But we know this is 180. So actually, if you actually notice, this gap here between 90 and alpha, that's kind of the same gap between 180 and this solution here as well. But the only thing we changed really was adding 90, really. And in general, a sine graph is you get a cos graph and then you add 90 onto it to get the sine graph here, right? Uh, but in general, that's what, in particular, with this sort of sine graph here, minus k. Let me draw that a bit. Let me try and draw that be a bit more like clearer to see, I guess. So we have there we go, some sort of graph like that. So 180 would be here, so then minus k would be here. So that's 180. So again, the Okay, hopefully you can notice the gap a bit clearer now. So 108 in here, but clearly that again that's the same gap between 90 and alpha. But really, all I've done was added 180, right? Added 90 to both parts. So 90 will become 180, and then alpha will become 180 add alpha. Okay. So to get from 90 to this solution, I need to add 90, right? Um, so the solution. So yeah. So it's going to be alpha at 90, right? Which is going to be this bit here. Okay. It can be quite very tricky visualizing that, but hopefully that just sort of makes sense. Um, so again, it's 180 again here when it's 0, and that'd be minus k. And then the gap between the x in when it crosses the x-axis and alpha is going to be the same distance or gap here. Um, okay. Okay. Question 24. Again, we're going to solve another simultaneous equations now, but the dude lot asking is sometimes like a more weird simultaneous equations one. But again, this is where substitution is probably going to be your friend here, and this is why I don't like elimination really. So I said substitution. Well, there are two ways you can do it. You could say xy is minus 3. So then, say for example, x would be minus 3 over y. Then you substitute it into here. But actually, I noticed the top equation is, and that'd be fine if you did it all that, but it'd be a bit messy. But I noticed the top equation is linear. So I could then say x is simply y add 19 over 4. That's a lot nicer to substitute in. So therefore, I'm going to sub x then into this in the second equation, xy minus 3. Then I'm going to get y add 19 over 4 lots of y is going to be minus 3. Then I can expand it out to say y squared add 19 over 4y. And then I'm going to add 3 to get a 0. This is the quadratic now. I wouldn't recommend probably factor. Well, I don't know if it would factorize, but I think the best way with a fractional part like this is to just do the formula. So actually, weirdly, I think you are given the quadratic formula and the formula sheet. I think, but you're not giving it in normal maths. I find that really weird. Um, but anyway, even if you forget it, but you should remember it's going to be y is minus the b part, so minus. So this is a. So obviously a is minus 1. The coefficient. B would be 19 over 4, and C would be positive 3. So then y would be minus 19 over 4, plus or minus the square root of b squared, which would be 19 over 4 all squared, minus 4 lots of 1 for A, and then 3 for C, and then all over 2 lots of 1. And so then you just bung that into the calculator. And so firstly, consider the positive case. So the plus the square root of 19 over 4 squared minus 4 lots of 1 lots of 3. You get minus 3 over 4. And then if you just change the positive to a minus before the square root, you get the other solution minus 4, which is fairly plausible, I guess. Quite nice numbers. So those are two solutions for y. But then we need to again solve it for x. But we know that we know that x, remember, was y at 19 over 4. So then I'm going to say when y is minus 3 over 4, x is going to be minus 3 over 4 as 19 over 4, which would be minus 16 over 4, right? Which should be minus 4. Positive 4, because 19 is bigger than 3. Yeah, okay, positive 4. Um, and then when y is minus 4, then x is going to be, again, minus 4 add 19 over 4. Um, uh, and that will be 3 over 4. So that's our solutions, right? So our solutions are going to be either x is 4, y is minus 3 over 4 from this one, or x is 3 over 4 and y will be minus 4. Okay, that's our solution here. Okay, so I do recommend substitution with these sort of questions. Eliminate a variable. I don't know. Just substitute. I think substitute invite is clearly what you're meant to do here. And if you get a funky simultaneous equation like this, try and use substitution. Substitute one variable into the other in some way. Like I said, you could rearrange this one to say x is minus 3 over y. And then you substitute it back into here. Then you could say what? Well, minus 3 over y and what minus y is 19 over 4. Then to get rid of the y, you just times by y. So you get minus 3 minus y squared is 19 over 4y. Then you move it. Then you can move everything to the right to get rid of the positive to say. Then y squared add 19 over 4y add 3 equals 0, which is exactly the quadratic we get here. Okay, either rule, but it's just I don't know. I just find it looks a bit nastier, but it works out the same way. Okay, cool. Question 25. Okay, we are given the curve here again. We've only has 3 stationary points. Work out these stationary points and determine their nature. Okay, so stationary points. So that's going to correspond to when the gradient is equal to 0 specifically. Because a stationary point, for example, like a quadratic, it's the turning point. It's when particularly the gradient would be 0, so it's flat, right? If we drew a tangent, it would be flat, although it doesn't look flat in what I'm drawing. I don't know, something like that, right? It would have a flat gradient, so it'd be 0. So that corresponds to a stationary point or a turning point, okay? So every stationary point has to have gradient equal to 0. So let's work out the gradient. So dy dx then. Well, this is a nice polynomial, don't have to do anything with it. So x to the 4. So 4 has a coefficient of 1, if you will. So 4 times 1 would be 4, x to the 3. You're not 1 off the power. Then minus 18 times 2 would be minus 36, x. And then 2 minus 1 would be 1. So that's just x. There we go. That's quite nice. Then we need to set this to 0. How we can factorise, can't we? I can pull a factor of 4x out, because 4 is also common. So then I can say, well, that's going to be x squared minus 9 equals 0. And you could recognise this is a difference of 2 squares at this point. But you could just say, well, x is 0, or x squared is minus 9 equals 0. Therefore, x squared is 9. So then x is plus or minus square root 9, which is plus or minus 3. Either or doesn't matter. But we've got 3 solutions now. So we've got x is 0, 3, minus 3. Okay. Well, we need to find the coordinates. Okay, so that means so we need to find the y coordinates as well. So that means when x is 0, y is equal to 0 to the 4 minus 18 of 0 squared, which should be 0. When x is 3, y would be positive 3 to the 4 minus 18 to the 3 squared. I put that into the calculator. You would get 3 to the 4 minus 18, 3 squared, minus 81. Now, this was a non-calculator question. It's not too bad to work out without a calculator, but just to speed it up, and because you would have a calculator, there's no point doing that here. So 3 to the 4 minus 18, 3 squared gets minus 81. Then when x is minus 3, y would be minus 3 to the 4 minus 18 of minus 3 squared. Now, actually, these are even powers. So actually, this is going to be the same as positive 3 here. Which should still be minus 81, okay? Because 3 squared, 3 to the 4, 3 to the 6, 3 to the 8, you're squaring, you're basically squaring, and if you square negative, you get positive, so it'd be the same coordinate, but you can just put it into your calculator. So we have our points, so therefore, stationary points are the coordinates are x is 0 and y is 0, the origin, I guess. Then when x is 3, y is 8 minus 81, or minus 3 minus 81. But we're not done there, because then it's asked to determine their nature. So that means you then need to consider further, well, a stationary point can either be uh, let's draw it, a minimum. So when the curve dips like this, like a quadratic, has a minimum point. It will either have a maximum, so it goes the opposite way around. It shoots up and back down, so it has a maximum point, the maximum value, or I'm not going to talk about the other one. I'm not sure if it's on the spec, but let me just. But either way, what that corresponds to, these minimum maximum points, it corresponds to the second derivative. Okay, so we're going to need to differentiate again. So we know that dy dx is 4x cubed minus 36x. So then d squared y, the second derivative, that's going to be equal to 12. Again, 3 times 4 is 12, x squared, knock 1 off, minus 36, okay? X to 1 times 36 is 36 times x to the 0, which is 1. Okay, but there we are, that's the second derivative. Now, what we need to do is to substitute each of these points, x is 0, x is 3, x minus 3, into the second derivative. And you need to pay attention to the sign. Okay, so what I'm going to say is, well, first of all, sub x is 0. Then we're going to have 12 of 0 squared minus 36. That's going to be minus 36. Now, this is negative. So this is going to be a maximum point. So it's going to look like this, okay? Do I want to explain why? Okay, the second, as I discussed earlier, the second you could just memorize essentially maximum. Let me do it here. So maximum when the second derivative d squared y dx squared is less than 0, and the minimum will be the opposite. So minimum when obviously the second derivative will instead be greater than 0, so positive. You could memorize that. But what's going on here? The second derivative. So I said about this earlier. The first derivative is a rate of change. So then the second, so and the first derivative is all about the gradients around the point, right? So then the second derivative is the rate of change of the gradients. So if we plot the gradient around, say, this point here, so it's going to be here and here. Oh, short again. Oh, for God's sake. Oh God. Let's draw it here. So it's going to be like here, and then here, and then it goes to 0, and then it goes down there, and then it goes down there. What you notice is the gradients are going like this. So it's going up, then it's going flat like this, and it goes flat, and then it goes down. So it's going from a positive gradient that's going up to a negative that's going down. If you're going from the positive to the negative, the rate of change is a negative, okay, which explains why the second derivative must be 0. The gradients must be going negative around the point. The opposite argument here for a minimum, again, the gradients are going negative, and then it's going to 0, but then the curve shoots back up, so the gradients go from negative to a positive, right? So the opposite effect. So they're going from negative to positive, so the change is positive. So it's going from negative to a positive. So the minimum is a positive. Okay, but that might be a bit abstract for this, I think, for GCSE. But you just need to memorize these two conditions, I believe, uh, about minimum and maximum turning points. Okay, let me get rid of this now. It looks a bit weird. Uh, okay, so a minimum would be here, and obviously a maximum would be like this. Okay, cool. So therefore it's a negative, so it has to be a maximum. Then we're going to substitute the other point in. X is 3, and so then the second derivative here is going to be 12 lots of 3 squared minus 36, and that's going to get us 72. So it's positive, so it's a minimum, right? And then I'm going to substitute the last point in. I'm going to squeeze it in. X is minus 3. Now, so that'll be 12 of minus 3 squared plus minus 36. Now, in the same way, because we're squaring upon negative, it's the same as the positive. So this will also be 72. So it's a positive again, so a minimum. Okay. Um, and so actually then what we've done now is use the second derivative to determine the nature. So the nature means is it a minimum turning point or minimum stationary point or a maximum. So you need to consider the second derivative and the signs, okay? Um, and so I guess if we were to wrap this all up, oh, I don't have space. Can I make space? Let me have a look. Okay. Okay. Not ideal, but there we go. So remember our points. Remember 0, 0. First of all, here, that's stationary points. But their nature, then, remember when x was 0, so down here, we got a negative, so we conclude it's a maximum. So this is a maximum, okay? The other stationary point is 3 minus 81. Again, that's going to be here. And we said that's a minimum, okay? And also, the minus 3 minus 81 is also a minimum because they're both having positive derivative. Okay, and there we are. Oh my God, what a question. That'll probably be towards the end of the paper, but you just need to remember how to spot that, okay? What it means by stationary point, what it means by nature. So stationary points when the first derivative is 0 here. And then the nature is if it's the maximum or the minimum. So you need to differentiate again, the second derivative, and then look at the sign if you substitute the x point in. Okay. Oh man. There we go. Okay, last question now. And this was the last question. I'm going to get rid of this now. But the final question. And this was a final question. It might come up. A similar question. I don't know. I did notice they do love asking final questions with algebra like this. So let's have a look. So using powers of 2 or otherwise, work out the non-zero values such that this happens. Okay, well, it's not particularly nice, but like I said before, let's simplify the left and the right hand bit side separately. And I'm going to probably use index laws, right? So first of all, 16x to the x. Oh, all x. Um, firstly, well, I guess you could say that's 16x times x, but x times x is x squared, isn't it? So that will go to 16x squared. Uh, okay. Okay, you might not spot maybe what to do at the moment here. Okay. But then let's do the right hand side. So 1 over 2 to the 3x. Well, there's not a lot you can do here, but clearly this is a reciprocal, isn't it? So this can be 2 to the minus 3x. So that means then I have to say 16x squared is 2 to the minus 3x. Uh, But how, oh no, 16 of x squared, sorry, not 16 times x squared. But it's not explicitly clear how we can compare it. But then I should know, well, 16 is a power of 2. It's 2 to the 4. So then I'll say, well, 2 to the 4 of x squared is 2 to the minus 3x, which makes it a lot easier. And then, again, because of the index law, if you have a bracket times our power, we can times the powers together. So that's going to be 2 lots of 4 times x squared. That's 4x squared is 2 to the minus 3x. Now I can compare them because they have the same base with the same number. So if the numbers are the same, that means the powers have to be the same as well. Therefore, 4x squared has to equal minus 3x. Then 4x squared add 3x equals 0. Then we need to solve it, right, to find x. Well, how to solve it? Well, just factor an x out, can't we? Then we can say it's 4x add 3 equals 0. Therefore, simply x is 0 or 4x plus 3 is 0. So each factor, each multiple has to be 0. Then that would mean x is minus 3 over 4. So we've got two solutions. There we are. Then it says the non-zero value of x. So that means x cannot be 0. Therefore, the only solution is x minus 3 over 4. There we are. Great. And that's the end of the page. That's the end of this session, really. I've got all the questions I've got. Um, yeah, I will load this now as I can. But hopefully it made sense. But yeah, as I said from the paper, I'd expect a lot of matrices and a lot of differentiation and probably some solving equations. I think they did a lot of geometric stuff in paper one. But who knows? Again, make sure you learn everything. But I think I think I've covered a lot of like the more further mathsy stuff in this paper, like the differentiation, the matrices, some of the stuff about sequences being limiting, converging when it goes to infinity and stuff like that. Um, but yeah, so I guess I'd say good luck, but I'm going to leave that there.